So, before we proceed, okay, did you understand yesterday quasi continuous wave, pulsed Q switched approach? Of course, how to achieve Q switching you may not be able to find out exactly, but quality right factor in the cavity is taken care, and its operations are very much at microsecond level or within the lifetime of the upper state lifetime, right, of the laser right levels, energy levels. So, in the case of neodymium YAG laser, it is around 230 microsecond or so. And before we go to mode locking approach, one more approach is there, just it is very simple, it is known as gain switching approach. Okay. For this gain switching approach is basically for those lasing or laser materials, okay, to achieve pulsed narrowing, okay, pulsed width narrowing, output pulse narrowing, as well as right short pulse lasers. So, this gain switching approach is for those lasers whose upper state. When I say upper state means laser levels, if there are 4 energy levels, this is up, pumping, band, pump band, and there will be a fast decay. Okay, so there will be a fast decay, there will be a fast decay over here, and the laser operation is between these two levels. So, this is upper level, okay, for lasing upper level, and this is ground level, sorry, lower level, okay. This is ground level, of course, this is pump level, correct, and what we achieve is amplification at this wavelength, right, amplification, and here the excited state atoms are many more, correct, because whatever comes fast decay to this position, this level, and then it this level remains empty approximately because of the fast decay to the ground level. Hence, and this is highly populated, right, this level, and it is also metastable level. Metastable level means it has a longer lifetime, so that spontaneous emission is quite slow, correct. And in case of neodymium YAG laser, as I told you, it is around 230 microsecond, okay, lifetime, and we use Q switching out approach for such lasing materials. However, if you consider titanium sapphire, which is another tunable solid state, which is a solid state laser, but it has a tunable range. And secondly, the lifetime over here, okay, the lifetime of this energy state metastable this level is approximately 3 to 4 microsecond. Okay, it's very small, lifetime is quite small, shorter. Okay, so if the lifetime is shorter, what it means that the Q switching becomes quite difficult to operate. Within this lifetime, Q switching has to be operated, then only the quality factor will change and a narrow pulse laser output can be achieved. But since the lifetime is quite short, it becomes quite challenging, okay, in terms of Q switching output. So, what is used? The technique used is gain switching. Okay. In case of gain switching this approach, the titanium sapphire laser is pumped with another laser which is also a Q switched pulse laser. Okay. So, first of all, titanium sapphire laser, the pumping wavelength for titanium sapphire laser is around 500 nanometer. which is green color around 500 nanometer, okay, which is green color. Okay. Green color means of course second harmonic of neodymium YAG laser, which is SHG wavelength is around 532 nanometer, correct. So, I can use or we can use Nd:YAG laser, second harmonic of Nd:YAG laser to pump this titanium sapphire laser. So, the input wavelength is 532 nanometer. This is let us say Q switched laser, correct. Nd:YAG laser can be Q switched. So, the pulse width is 5 to 6 nanosecond, correct, pulse width. So, that means within 5 to 6 nanosecond the titanium sapphire laser upper this laser level will get populated, correct. All the pumping energy will be used to populate this metastable level in titanium sapphire crystal. It will get populated within 5 to 6 nanosecond, very short. So, automatically the output what we will achieve will be of the nanosecond order, because then the cavity will ensure that all the photons are extracted at a corresponding to the laser wavelength. So, here very short. So, in terms of time duration, right, Nd:YAG laser is 5 to 6 nanosecond will pump the titanium sapphire laser, and within a very short period of time the titanium sapphire laser output can be achieved, right. And then till the second pulse comes from Nd:YAG laser, the titanium sapphire laser output is not, is not it, and the pulse width may be of the order of 10 to 20 nanosecond, or maybe depending upon the gain etcetera, the pulse width may slightly it will get little broaden up to 10 to 20 nanosecond. Okay. So, this is known as gain switching. So, first you allow using the pump pulse X populate the upper state of the upper laser level state to a very high this population density, and then there is no other pump pulse coming into picture, it is only the lasing action which will take place. So, within a very short time you are pumping, we would like to pump, and that is why its gain is switched to this output. So, this is one technique. However, we also would like to see there is one more technique which is known as mode locking technique, and the mode locking technique allows ultra short pulse laser output. Okay. Okay. So, what it means ultra short pulse? When we say short pulse laser output or pulsed laser output, maybe Nd:YAG laser means few nanoseconds, as we already discussed 5 to 6 nanosecond, or if it is titanium sapphire laser maybe 10 nanosecond, 20 nanosecond, these are all short pulse. 1 nanosecond is of course we know which corresponds to 10 raised to minus 9 second, correct. So, the whole pulse energy is extracted in such a short period of time, 5 to 6 nanosecond, right. Hence, the peak power is very large, and it has various applications, but ultra short pulse means further down, okay, to picosecond, sub picosecond, femtosecond level. Okay. Picosecond means 10 raised to minus 12 seconds pulse width, femtosecond is 10 raised to minus 15 second pulse width. Okay. It is very short pulse laser. It has some specific application in biophotonics area, particularly interaction of such laser with the tissue has a different effect. Okay. Very less thermal effect, and damage to the tissue is quite low. Okay. You may think that the peak power would be very large, is not it, 10 raised to minus 15 second. Even if the laser energy pulse output energy is 1 millijoule, okay, let us say output energy. I am just giving you an example just to get an idea in terms of what is the peak power. So, if the output energy of a particular laser, let us say it is 1 millijoule, right. So, it is 10 raised to minus 3 joule, okay, and the pulse width, let us say it is 100 femtosecond pulse width. Okay. If the pulse width is 100 femtosecond, then it is 100 into 10 raised to minus 15 second, right. So, what will be the power per each pulse which will be, right, emitted from this laser system? What will be the power? It is equal to right 10 raised to minus 5 10 raised to 10 watt, correct, right, 10 raised to minus 5 10 raised to 10 watt. What it means? 10 gigawatt, okay, 10 gigawatt is the power, peak power. You can imagine, okay, right. Do you know what is our Tamil Nadu's power requirement? Summer around approximately, no idea, 1200 1300 megawatt, okay, right. So, one few gigawatts total, right, 1 or 2 gigawatt. This is one pulse of laser, 10 gigawatt. That means, so all power stations will close down? No, nothing like that, isn't it? The energy is very low, it is only short energy is extracted in a very short period of time. So, the power per pulse may be very large, energy used is very small, is not it, energy which is it okay? So, you can imagine that if it is millijoule becomes joule, automatically you can imagine that it can go up to terawatt output in power, peak power, which is very large, okay, and within a short period of time you are delivering the energy. Now, coming back to our understanding about how to generate such ultra short pulse laser, right. A Q switching has a limitation that it cannot allow shorter than nanosecond, because the operating system is such that, okay, and it is very difficult to operate with a very short, right, Q switching duration, etc., right. Control of the Q switching in a less than nanosecond, sub nanosecond level becomes much quite difficult. So, the technique which is used and is mode locking technique. And now, another aspect, based on the we know, based on the Fourier right transform, we know that pulse duration and the spectral bandwidth has some relationship, right, in terms of a electromagnetic wave. The pulse duration becomes shorter and shorter, which corresponds to the spectral width becoming wider in the laser. Okay. So, if the gain bandwidth of the laser material is not wide enough, we will not be able to achieve very short pulse laser output as well. Okay. So, let us say if we are considering neodymium YAG laser, the spectral width is less than nanometer order, okay, spectral width of the laser. So, output wavelength, when we say 1064 nanometer, it will have a spectral bandwidth just 1 nanometer, okay, width or less than that. But if we are considering titanium sapphire laser, it has a broad gain bandwidth, as we already know. That means there is a possibility of achieving shorter pulse width with titanium sapphire laser. Okay. Now, so how to achieve this is basically the technique which is known as mode locking is what? See, when we consider a laser cavity, let us say this is a laser cavity which has a titanium, let us say sapphire crystal. Okay. So, let us say this is a titanium sapphire crystal, okay, and now you are pumping it. So, let us say there is a pumping of this crystal with a green color, right, pumping, it is getting excited. Now, it will emit many photons, and since it is having a broadband gain width, it will emit photons with different photon energy or wavelengths, correct, different photons wavelength within the gain bandwidth, and some of these photons will be able to, some of these wavelengths will be able to oscillate depending upon the laser cavity length and mode spacing decided based on this, which we already know. Now, that means different wavelengths will be able to oscillate, okay, in this cavity, which satisfies the mode spacing, correct. Delta this new mode spacing, which is C by 2L, which satisfies this, will be able to oscillate, and gain bandwidth is much wider. That means many of these modes will be able to oscillate, okay, in this cavity, they will all be able to oscillate. Hence, its right gain bandwidth is wide, so many modes are going to oscillate. Now, all these modes when they are oscillating this, the output, if we try to see the output intensity or in terms of electrical field amplitude, of the electromagnetic wave or subsequently intensity, if we see in terms of electrical field amplitude, addition of all these waves which are oscillating with different frequencies, nu 1, nu 2, nu 3, nu 4, let us say nu 5, nu 6, like that there are many modes will be there, okay. This is just I have many such modes which are oscillating, and electrical field, if I add up in terms of time, and if I see the output, what will happen, all of them, V nu 1, nu 2, nu 3, nu 4, nu 5, nu 6, all these wavelengths will have different phase, right, at it is not controlled, correct, there is no phase control. Of course, all new ones which are emitted may have similar phase, but nu 2 may have slightly different phase, okay, because they are all independently, right, oscillating, right, photons. That means, our output will be sum of all this, right, electrical field with different phase. So, the addition right will end up with some average output, okay, average output, and if we try to see intensity, which is proportional to E square, right, E square, electrical field square, that is also not very large, okay. So, this is right the general right outcome, okay. The output power will be, if you add up in terms of intensity some of this electrical field, it will be very small average power based on the all the modes which are add up all this, right. However, if we control the cavity such a way that all these modes, okay, nu 1, nu 2, nu 3 modes, or lambda 1, lambda 2, lambda 3 wavelengths, all these wavelengths which are emitted have the same phase, okay, right, at a particular point, okay, they have the same phase, okay, same phase, all modes. In general, when there is no control over the cavity, all of them are emitted with, let us say nu 1 is emitted with one frequency and has certain phase. At the same position, maybe nu 2 is emitted separately and it has a different phase, okay, like this. And when you add up amplitude wise electrical field, you will end up with a right very small output. However, if all these waves at one particular position here, let us say they have the same phase, one lambda 1 has this, lambda 2, although wavelengths are different, slightly different because of this right frequency spacing, wavelengths may be different. Okay, I said okay. So phase is same, right, phase is same. So here let us say sorry, it is, I should draw it nicely so that you can get convinced. Okay, that some other wavelength may have okay, all these waves with frequency nu 1 or lambda 1 wavelength, nu 2, nu 3, they have the same phase. Then electrical field what will add up will be quite right larger, right, it will add up quite larger. And what will happen, this phase as it goes away as it goes away will change, right, all of this because wavelengths are different. So, automatically at one point they are phase matched, but at another points they are all out of phase, but when they complete one round trip again they will be at the same phase, okay, because this cavity will only allow those modes to oscillate which are forming standing wave pattern. So, that means they will complete the one full cycle, they will come back to the original same phase at one round trip. All of them will add up at one position, otherwise there will be right different phase. Are you clear? Okay. So, this phase matching of all these waves by some means, right, is nothing but you are locking all the modes with the same phase. Okay. It is known as mode locking. Okay. Now, you may think how will I achieve right such a control of so many frequencies are oscillating depending upon the laser cavity and all this. Now, how will I ensure that all these phases are at the same right matching with each other. So, this phase matching right how to achieve is right it is another right approach technique, but you know that saturable absorbers which I told you that they will be opaque for certain intensity. As soon as the intensity increases they become transparent because of what, two level energy systems getting saturated, isn't it. So, if I use a material with a very short such lifetime of saturable absorber lifetime, right, then unless the intensity of all these modes or sum up additional intensity becomes much larger, it will not open up, right, it will not open. So, it will not it will remain opaque till all the frequencies are oscillating with different phase, and let us say this is saturable absorber, this is saturable absorber. Okay. All these waves add up electrical if they are of different phases nu 1, nu 2 etcetera of different phases, the overall intensity is not very large, the material this saturable absorber may remain opaque, but when the intensity increases to the extent that it is matching approximately matching with when the all phases are equal, then only this will become transparent. Okay. So, initially when such oscillation starts they are all random, but slowly right they are all random, but there will be few photons of different frequencies and their phase may approximately come nearer and match with each other within a certain range, then the electrical field will amplitude will increase, intensity of the light, overall light within this cavity will also increase at this position 1, then this material will become transparent. Okay. So, of course, we rely on some chance of such thing happening. Okay. Right. So, that is one method. Okay. Another method is known as Kerr lens effect. Okay. Kerr lens effect. So, so that effect is such that the crystal titanium sapphire crystal is also acting as that Kerr lens effect. So, depending upon the intensity of the laser, okay, the refractive index of this material titanium sapphire laser changes depending upon the intensity of the light intensity. Okay. So, if the light intensity is large, then refractive index in the, let us say in the center, if it is large, it will have large refractive index in the center, and the beam at the outer periphery will have lesser intensity, then it will have less refractive index. So, basically this material will act as a lens. Okay, it will act as a lens. So, the more the intensity, the lens effect in this crystal, right, will be much larger. So, what it means, the beam, incoming beam, light beam will start focusing. Okay, it will start focusing somewhere, okay, because of this lens effect. So, if I put one aperture over here, very small aperture, which can only allow when the intensity is large enough, then the light, focused light will pass through. Okay. Otherwise, if the intensity is not large enough, lens effect is not seen. So, whatever beam comes in will pass through, and aperture will restrict its intensity or energy. Okay. So, if this energy is very, very small, the losses, the gain will, right, the laser amplification will have very less small output, and which is not mode locked output. But at one point of time, as this effect comes into picture, as the modes starts aligning themselves with each other with multiple such rounds, from the small number of photons which are coming back, right, through the aperture, passing through the aperture, coming back, with that slowly the intensity increases and it reaches to a particular point wherein the whole energy will pass through this because of the focusing effect. Okay. And that will happen when all these modes are approximately in the same phase. Okay. And then only at one particular position, okay, and then only the intensity will add up over here, okay, and the lens effect can be observed. So, these are all approaches which are used to shorten the to add up this. Now, if you can see that as this number of modes are large enough, and if they are in the phase at one position, they will all add up in terms of intensity with right time versus intensity. If you see, it will have a very sharp peak, then another sharp peak after one round trip. So, one round trip in terms of time is equal to 2L divided by C, right, speed of light. L is the round trip. So, time taken for one round trip, right, in the laser cavity of length L is 2L by C. Now, this pulse which is sharp enough, its energy is electrical field adds up right constructively, and intensity which is proportional to E square will be very large, and as soon as the other right after this point phase will be different, phase for each of this wavelength will be different. So, the overall intensity of this will be quite small, okay, was quite small over here, okay, as similar to this intensity without mode locking, correct. So, very small output and very large peak power at mode locked condition, okay, will result in such right such peaks, okay, and spacing is 2 L by C, round trip cavity round trip will be the spacing, and the pulse width of this will depend upon pulse width will depend upon gain bandwidth. This gain bandwidth is nothing but this, okay, gain bandwidth, total spectral bandwidth of this, okay, will depend upon this. Okay. So, the broader this spectral bandwidth, the pulse width will be shorter and shorter, okay, and you can imagine, right, you can estimate for lambda equal to, let us say, for titanium sapphire laser lambda is 800 nanometer, right, in terms of let us say spectral bandwidth it is, let us say, 600 nanometer to 1000 nanometer, which is a right here to here, maybe approximately, let us just I am taking, let us say, delta nu for type of cavity what we use, maybe it is around 100 nanometer, let us assume delta nu. Now, you can easily estimate what is delta lambda is 100 nanometer, what is delta nu, you know, right, relationship between delta lambda you will be able to estimate what is the spectral bandwidth in terms of frequency, right, and then the time can be estimated, right, pulse width time is equal to almost equal to 1 upon delta, okay. So, that is the way that we estimate, and this turns out to be, if you estimate, it will turn out to be sub picosecond or picosecond order also, okay. So, quite narrow pulse width is achieved. So, now we know overall about types of lasers, spectral narrowing, which is related to spectral width, and pulse narrowing, which related to output pulse width, okay, all these aspects that we know. So, one more aspect which I wanted to provide you some input about the laser beam characteristics. Okay. What I talked in the previous few classes is spectral characteristics, pulse characteristics, is not it, a laser. Now, laser beam, this is basically a spatial intensity distribution, spatial characteristics. So, if you consider a laser beam and if you take a cross section of that laser beam and see the intensity distribution, right, and that is what we would like to see. So, generally the laser beam possesses means it has a Gaussian beam profile, okay, Gaussian beam profile. Okay. So, if you take a planar wave front, okay, of the light propagating this, if you take a planar wave front of the light, then you will see that light will propagate with intensity distribution which is planar, because it has all planar waves, okay, wave fronts, which is will be the planar wave front. And if you take a circular wave front, that means from a point source the light it will intense as it goes away the wave fronts will keep expanding with radius, and Gaussian beam profile is somewhat a combination of this. That means, at a beam waist position it is planar wave front, okay, and then slowly as the beam propagates along this z direction, right, it is slowly it's becoming okay, it becomes like this. Okay. So, the radius of curvature changes, right, and finally it becomes circular, right. I mean, from the planar wavefront it is becoming like this circular wavefront, okay, and the divergence, right, of the beam, right, is like this, okay, right, divergence of the beam is decided by this way, okay. So, this and if we take the cross section of this laser, if we take the cross section over here, let us say we cut the laser beam and see this is z, seen the xy, right, the plane, what is the energy intensity distribution, we will see this. So, first of all this divergence is also Gaussian in shape, okay, Gaussian shape. Over and above the cross section is having a circular beam profile, but it is Gaussian in shape in terms of energy distribution, okay. So, if I take a cross section over here and see through, okay, in this plane and see its sorry, if I, right, in terms of radial distance, okay, radial distance, if I see. So, at this point where r is 0, intensity will be maximum, and as you go away from this, right, position, the intensity decreases, and this intensity is, let us say this is I 0, I r is I 0 at max, right, position to exponent of minus 2 r square by w square, okay, 2 r square by w square. What is r is this radial distance, right, radial distance, and w is the beam waist, w is the beam waist where intensity is 1 by E square, is not it. When r becomes w, intensity will become in I 0 by E square, is not it, I 0 by E square, is not it. So, where intensity of this beam profile becomes I 0 by E square, the r value is nothing but the beam waist, right, this beam waist, is it okay, approximately, right, it is. So, and this profile, this is a Gaussian beam or normal, right, distribution, Gaussian beam distribution, okay. So, if I let us say cut the beam over here section, okay, and if I see through, okay, over here, what will we observe? Similar to this we will observe, okay, the beam profile. However, it may be little wider, is not it. Okay. So, this is, let us say at this position pick I 0, then this beam support size at w, this is at w 0, z is 0, correct, z is 0 here, it is at some distance z, right, beam support. So, this will become w z, right, beam support, right, which is much wider than w, okay. So, as this beam propagates, divergence comes into picture, the beam characteristics are like this. Is it okay? So, if I try to express in terms of beam, right, size, etc., or maybe there is a picture. So, whatever I explained here, if I have the slide, let us see. Oh, it is not there. It should be there. No, it is not there. Okay. Anyway, what I explained is right. It's so every this point. Once again, so here the beam support is circular, but its intensity distribution is like this. Here the beam support is also circular, but much bigger, right, much bigger beam support, right, much wider, and the intensity distribution at the center, it is high intensity and then it tapers down, decreases, right, with Gaussian beam shape characteristics. So, as we go further, the beam support size increases. So, at the position where we observe the minimum beam waist, which is at this position z equal to 0, this is known as beam waist, and at any other positions wherever we observe this W with, right, at different positions, they are known as beam support size. Okay. So, W z is beam support size at, so at z equal to 0, beam support size is nothing but beam waist, smallest possible, right, radial diameter of this, right, while at any other position it is known as beam support size. And the relationship, right, between W z, considering a Gaussian beam shape, the relationship is between W z and W at 0 is W z at any position z is beam waist W 0 at z equal to 0, okay, 1 plus lambda z upon pi W 0 square this is the configuration, okay. And so, right here, so W 0 is where z equal to 0, right, which is nothing but the beam waist, and W z is beam support size. Okay, one more minute, just, and at, let us say, okay, at the position where W 0, okay, or sorry not W 0, okay, W z becomes root 2 times W 0, okay. So, beam size becomes, beam support size becomes root 2 times the beam waist, okay. So, area becomes double, is not it? Area of the circle A is pi by 4 pi r square. So, root 2 W 0 square, right. So, at beam waist, area at beam waist is pi W 0 square. So, area at certain position z where W z becomes root 2 times W 0, the beam will become two times, sorry, pi, correct, it will be 2 times. So, at the position where this becomes, at the position where beam size becomes beam support size, that distance z is known as Rayleigh range ZR, okay, ZR. So, if I substitute this in our previous equation and estimate the distance z, okay, in this equation where W z becomes root 2 times W 0 and I estimate the z, then z which is known as ZR Rayleigh range, okay, will be equal to pi W0 square by lambda. Okay. So, this one. And right. So, beam while propagating, it propagates like this, right. In the center it is W0, this is Z, this is laser beam, and it as it goes along Z, W0 increases at a position where WZ R is root 2 times W0, okay, like this. So, this distance is ZR, correct, or right, and this distance is 2 times ZR, and this 2 times ZR is known as cone focal parameter. Okay, parameter. These are all terms, definitions. ZR is the Rayleigh range, double this, and these terms are useful to determine the depth of focus. When you focus the beam up to root 2 times of the W0, you consider approximately the same up to the right. So, this part you treat it as a one cylinder, something like that, okay, approximately. Of course, it is approximation that the beam size is approximately okay within small limit, it is increasing or changing, and this. So, this is confocal parameter, and maybe next class we will proceed from here. Okay. Thank you very much.